And we're live. Over to you.
Okay,
That's it.
so today we're looking at Mechanics 1, which you've had a look at before. Now, most of these questions are going to be blocks on surfaces, blocks on ramps, balancing forces, and a couple of kinematics questions. So the very first one is about as simple a setup as you can hope for. Simple block resting on a plane. Step one is always to draw a diagram, no matter how simple the question. You never know, they might try and trick you out. So you've got your block on a plane, and you draw all the forces involved. So if it's sitting still, which it is to begin with, what forces are involved? Well, you've got the weight of the block always, which is going to be mg. And because it's not falling through the floor, it must be in equilibrium, means the forces in all directions must be balanced. Therefore, you must have an equal and opposite force. We call the reaction force R, or sometimes the normal force N, so on, which is also equal to mg. There are no forces on either side. All the forces are balanced, otherwise the thing would be moving. That's Newton's laws. So it's completely in static equilibrium. Now, the key equation for the first question is this one, to do with the force of friction. Force of friction is equal to mu mg. Well, actually, sorry, that's actually deceptive. It's mu r. Now, in this case, r is mg, but if you were, say, sitting on the block, it wouldn't just be the mass of the block, it would be your mass, or if you were standing next to the block and pushing down, the reactive force would also include that force. So it's best to write it as mu r, so we're clear. In this case, r, and usually in these questions, it will just be the weight of the object. So we've got a surface, this mu, which is a Greek mu, represents the coefficient of friction of the surface. So you see that if mu is greater than 1, the force of friction is going to be greater than the reactive force. Now the reactive force is just mg, so therefore the force of friction is greater than mg. Therefore it's going to take more force to make it move horizontally than it is to make it start rising. Because all you'd have to do then is lift it vertically, there'd be no friction to account for. Let's highlight that mu. And that's all that's required of the question, 2 marks, no problem. So now they're saying we're going to start applying a force of magnitude p, and let's just pick the direction of the force to be like this. Could be either way, it doesn't matter where you're standing. Now we know that the force of friction always it opposes motion. So nothing we're doing is going to make it move to the left, or the motion is going to be to the right if there is enough force to induce motion. So the force of friction must be in the opposite direction. Force of friction. So the key to all of these problems really is to resolve the forces along different axes. You pick your axis to be the most convenient. There could be anything. There could be something like absolutely nuts, like over there, but then you'd be dealing with loads of trig and, it's just not worth your time. You're obviously going to pick the x-axis to be like that and the y-axis to be like that, because it maximizes the number of forces that are actually along the axes. And that's always what you're looking for. Sometimes here, all of them are along axes. Sometimes you won't be able to do that, but you want to maximize the number because it makes it simpler. And the key idea is that forces along different axes are completely independent. So you can talk about the force in the y-axis and the force along the x-axis, and these will not affect each other in any way. So we're looking at horizontal movement. So let's call this is P, newtons. And okay, it's good to keep track of units. It can often help you from stop you from making a mistake. Later on, if you realize you've got the wrong units, you've obviously forgotten something. But I will say, when they're marking, they're not too fussy about the units. Just make sure that if 2 things are in centimeters and meters, you turn them both into meters or something, so you don't get the wrong order of magnitude. But actually, having the units in your final answer isn't that important in these papers. So we're going to look at the forces along the x-axis, because the ones along the y-axis are completely balanced. We don't care. There's going to be no movement. So we're going to say the force along, the x-axis, the net force. We're going to define this direction from left to right as being our positive direction. It's completely arbitrary as long as you're consistent. And you pick that to be your positive x direction, and always do with reference to that, you won't run into any problems. You could say negative, but in this case, it's always convenient to define it as the direction that you can actually have movement. So the only force pointing in the positive x direction is P, and the only force pointing in the negative x direction is the force of friction. So P we don't know, force of friction we do know. We can solve for P if we know the net force in the F direction. Well, what we're told is the acceleration. So all we have to do is use Newton's second law. F equals ma. We know the mass, we know the force of friction, we know the acceleration, we can solve for P. And that's all there is to it. You plug it in, you get the value.
Cool. Did you get that one okay, guys? Yeah. Quinn,
Yeah.
you get that? Brilliant.
Okay, so the next question is one of these ramp problems, which come up a lot. Now the key to ramp problems, I'll just give you some general advice, is always draw a diagram, but you already know that. You draw your ramp, and you know that this is the angle that they've given you, say alpha. You have something sitting on top of it. It's going to have a weight pointing straight down. You now want to pick your axes to be parallel and perpendicular to the ramp, not up and down in a normal way. So the first thing you have to do is resolve the weight along these two axes. So this one kind of goes like that. That's how the vector is made up, but it's affecting the object like that. And you can work out through very simple geometry that is also alpha. And use trigonometry to realize that the force into the ramp for the weight is mg cosine alpha, and the force downwards is mg sine alpha. Therefore, you know that the reaction force is also going to be mg cosine alpha.
And how do you know that, Keelan? How do you know that it must be the same? Those green arrows must be the same.
They're both on the same line. They're both.
So yeah.
No,
What's Hannah using to instantly say that those forces must be the same? What idea is that? No, sorry, it's not a test. I just
No, it's
wondered if you knew it already.
I think the key idea is thinking back to that Newton's second law, that F equals ma.
Yeah.
Now, this is saying something quite profound. It's saying that if there's a force, a net force, there must be an acceleration. If there is an acceleration, there must be a net force. And this is true in independent directions, so there's independent axes. So, if there was a net force in the axis that sort of goes into the ramp, that's perpendicular to the ramp, then it would be moving along that line. It would either rise off the ramp in the sort of slanty way, or it would sink into the ramp. But since it's not moving in that direction, maybe it's moving along the ramp, but that's irrelevant considering this axis. So because it's not moving, acceleration is zero. Well, it's not moving and it's not about to move because there's no acceleration of any kind. It's moving at a constant speed, which is zero. Therefore, the force going in must be equal to the force in the opposite direction. And there's no other forces along this axis, unless they give you one. They might say that someone's shot a bullet in it, whatever. But in these cases, in these papers, there will be nothing more complicated than the weight of the object. So thus, we know that the normal force must be the same as the force in.
Nice.
So there will also often be a force of friction, which you must be careful now. Don't draw it in until you've realized which way the block will be moving. So in this case, there is nothing to pull the block up. So it will obviously start moving down because of the weight, in which case the force of friction would be like that. But if you had maybe a rope with a pulley, as we might see later, perhaps the motion might be in the opposite direction, in which case the force of friction would actually be like that. So just be careful, that can really catch you up if you make an assumption about which direction the force of friction is going before you know which way the thing is going to start moving. So this is essentially all you need to know. You know that the force of friction is also going to be equal to mu r. So you have that force for free from the weight of the object. Now, in this problem, we're just talking about, again, very simple, car. Here's our 2.5, I'm completely exaggerating this angle. There's a car, it starts over here, it ends over there, and they're asking they're asking you to find the speed. Now, you may automatically start thinking about the constant acceleration equations, and this falls under the topic of kinematics. Those are the ones which it's like S is equal to S naught plus VT minus 1/2 AT squared, all of these things. Don't use that unless you have to. The rough guide is, if the question asks you about the time, so how long something is taken, or how much time is elapsed, then you have to use kinematics. If it doesn't, you can probably get away with just using conservation of energy, which is way simpler. You don't have to worry about what happens in between 2 points. You just talk about the energy at each point. So our big equation for the conservation of energy, where in a universe where we have friction, is this symbol delta. And if you're familiar with it, it's capital Greek delta. It usually means change in something. So delta E means change in E, which we're going to say is energy. And I'm defining positive change as an increase in energy, which makes sense. It's going to be equal to delta K, which is the usual expression, K is the usual symbol for kinetic energy, or one of them, plus delta V. This is the potential energy, plus work. Now, this is where you have to be very careful. This is work done on the object, which makes sense. If I do work on the object, I'm sort of giving it energy. If it does work, it's sort of giving away energy. So we're talking about basically energy gained here. Kinetic energy gained plus potential energy gained plus work done on the object. Some textbooks define it the other way, with W meaning work done by the object. As long as you remember to think about what's actually happening, you won't go wrong. So, what's happening here? We have a mass we're given. This is going to come into our potential energy. We have resistance constant. The driving force is that. Speed of the car. Okay. So our initial kinetic energy, K naught, at the bottom of the hill, 1/2 m v naught squared. This is just the equation for kinetic energy. K prime. Prime is often used to, like, if you're talking about a second quantity of the same type. K prime is exactly the same, 1/2 m v prime squared. V naught, the potential energy at the bottom of the hill. Well, we just find this is 0 with reference to the top of the hill. We're only talking about changes in the potential energy. So it doesn't actually matter if the bottom of the hill is already 50 meters up on a precipice. We're only going to talk about, we're going to just say that the bottom has 0 potential energy. V prime, M, G, H. Those are the equations that you need to remember for the 2 different types of energy. Now, what we have is therefore delta K. In fact, well, delta K is equal to K prime minus K naught. Delta V is equal to V prime minus V naught. So that's all the delta means. It's like how this thing has changed, and you just have to make sure that the primes come first in both or second in both. You just got to keep an idea of directionality of the thing. So we know that the change in energy must be equal to 0 by conservation of energy. Now, I will just clarify that some people express this instead as saying delta E is equal to delta K plus delta V, which is equal to minus the work. So really, you get this equation is exactly the same as this equation, but in some they're talking about the change in energy being the energy sort of possessed by the car, in the sense, in which case it does change. Or you can think of the energy of the system, in which case the energy is conserved completely. They're just two different ways, but you end up with basically this exact same equation: delta K plus delta V plus W is equal to 0. So we get that K prime minus K naught, like let's, 1/2 mv naught squared, that's just delta K, plus mgh, and let me clarify, h is the vertical distance, which obviously is the only thing that matters when it comes to gravitational potential energy, is the distance from the center of the Earth, minus 0, because there was 0 at the beginning, that's delta V, is equal to minus the work done on the object. So what's the work done on the object? Well, the driving force does work on the object, pushing it forward. But some of that goes into the counteracting the resistance to the motion of the car. So so W should be equal to the driving force times the distance traveled. So this is another important equation, that work done on an object is equal to force times distance. And remember that you can kind of, this is a very helpful equation to remember units as well, because as we'll see a bit later, work is a unit of energy. It's an energy that something is being given. It's not a force itself. So it's measured in joules. Force is measured in newtons, and distance is obviously measured in meters. So you know that a joule is a newton times a meter. So our work here is the driving force times the distance minus, they've just given us straight off work, we don't have to worry about, they haven't given us a resisting force, they've given us a total amount of work of the resistance. So that's all you need to do for this question. As you see here, we know the mass, we know V naught, we know mass, we know the gravitational constant, which is, you can just approximate with 10 in these. We know the height, which is going to be equal to this length, which we were given, sine of 2.5 degrees. And we know the driving force, we know the distance, which is this thing here, and we know the work done by the resistive force. So everything is there. It just looks a little complicated, but you just have to plug it in. That gives us K prime, which is just equal to 1/2 mv naught squared. We know m, we can solve for V naught. And that's all there is to it.
Cool. Now the other way of doing it would be what? Which you don't recommend.
Right, so the other way to do it would be to use kinematics.
It's just longer, isn't it?
Oh, it's longer. It gets complicated and you often have to solve quadratic equations. You have you involve time, and then you get time squared, and then you find solutions to that. And we will see in the next question we do use kinematics there.
Well, my rule is if you can use energy, use energy. Yeah.
Absolutely. It's much easier to understand. You don't, it's much less opportunity to make silly mistakes, and it's much more.
And by energy, I suppose the main thing is just whatever you start with has to end up the same, right? And so as long as you make sure that it's called, as Hannah's written, it's the conservation of energy. It says that, well, you can't create or destroy energy. It must go into something. Either goes into raising the gravitational potential or increasing the speed, or it goes down into work against friction, which is really kinetic energy, isn't it? Really,
It's in part kinetic energy to the surroundings.
to the surroundings. Correct.
Yeah, but on this sort of macroscopic level, you can just think of it as being dissipated. But if you were looking at the system as a whole, the energy would, doesn't change. Work is just, one thing to another. It just.
Anyway, sorry, crack on. Excellent.
Okay, so this is a kinematics question. You can't avoid it. And how do we know that? Because we see this word length of time.
Yeah.
Oh well. So here's our setup. We have a cliff. There's an ocean there. Cliff is 40 meters. And in this first question, we say that the signal reaches an additional 5 meters high. In fact, in this very first question, the sub-question, we can use conservation of energy again. When it's fired, it has all kinetic energy, no potential energy. So E0, beginning, is just equal to 1/2 mv squared. E prime, the one at the very end, well, the thing is slowed down completely at the very peak of its arc. It has no velocity before it comes down again. So that's just equal to mgh. You know that this thing must equal to that thing, and so you can solve for v, no problem. You know everything else. So you end up with v is equal to square root of 2gh. You plug that in. The masses cancel out. You don't actually need to know the masses. So, but now we get to the length of time. Now the key formulas for this are in the formula booklet, so you don't need to worry. They're called the constant acceleration equations. Now, if you're familiar at all with integration, or if you become a bit familiar later on, there is a lovely, very pleasing proof of these. Just starting from acceleration is equal to the second derivative of the position. If you keep integrating that and keeping track of your constants, you will derive the constant acceleration equations. And you'll realize why they only work for constant acceleration. But at this stage, easier just to use the ones in the book. So I won't go over them. If we have time at the end, maybe I'll show you the integration method first, if you're interested. Now, when you have something that's thrown vertically upwards and then downwards again, you can plot a position time diagram, and it'll be a parabola, like so. Now here's worth emphasizing that the velocity is the derivative of the position with respect to time. S is used for the for position for reasons I think are related to general relativity.
Latin, isn't it? Maybe spatio or something means for displacement. Yes, maybe. Yeah.
There's the line element in GR.
Yeah. It's there to annoy you, because why would distance be called something beginning with S? It's just, but anyway.
I guess
know
they're called
that in
D.
German it's called Strecke.
There you go. So it's easy for you.
Loads of very famous physicists are German, like during the 20th century, so maybe it's probably it. We have eigenvalues.
That's probably why, yeah.
Okay, so V is ds dt, and the same strain, A is dV dt, which is equal to d squared s dt. So let's just think about what V is. Now, because it's the derivative of the position, well, the derivative is just the slope. So you can see that from this diagram. It gives you all that information. At the beginning, it's very, very steep, maximum acceleration, and at maximum velocity. As it goes up, it starts getting decelerated by gravity. So the slope decreases, i.e. the velocity decreases. Over here, at the very top of its maximum displacement from the bottom, the slope is flat. and therefore the velocity is equal to 0. And then it does exactly the same thing in reverse. So if you're just looking at something, forgetting about air resistance, forgetting about anything else, if you're just looking at something that heads into the air and comes back down, it will give you this parabolic shape and will be completely symmetric. So let's think about this as the path of the trajectory, and this straight line as just a line at the head of the cliff. That's just always at 40, and this is where it reaches at 45. So we're thinking about the times at which the signal passes the top of the cliff, because we want to know how much time it spends between these 2 points on a trajectory. Here it's at 40, then it goes above 40 for a while, and it comes back and it's 40 again. We only care about this period of time. So what is this? We want the coordinates of these 2 points. Essentially, we want the time coordinate of these 2 points. Well, what's that? That's just solving the simultaneous equations to find the intersection points of a straight line and a parabola. Well, how do we do that? We have our equations, and we set them equal to each other. Now, finding the equations is the important thing. Fortunately, in this case, it's not actually that hard. Firstly, let's think about our straight line. Very, very easy equation. S is equal to 40. No problem. There's no dependence on t for this straight line. The cliff is always at 40 meters up. The cliff doesn't change with time. What about the parabola? Well, here you use the constant acceleration equations. And this is it in general. S is equal to, so this is distance traveled. S is equal to, or distance above the ground in this case, S0, as in the initial distance above the ground, plus V0 times t, V0 being the initial velocity, plus 1/2 times the acceleration times the time squared. Now remember, this is only valid for constant acceleration. The integration will show you why. So in our case, S0 is 0. So we just have V0 t, and then A is actually minus g, because our directionality that we have chosen indicates that up is positive. But the acceleration, it's a vector, it has a direction, so it's actually acting downwards. So it must be minus g. So we have 1/2 minus 1/2 g t squared. That is the equation of this parabola. So we solve, we set it equal to, we know V0, so we don't have to worry about finding out, we just found in the previous question. We know G, and then we set these two equal to each other. We get the equation, blah, blah, blah. You can do it yourself, t squared minus 6t plus 8 is equal to 0. And this gives us the solution. There's two possible solutions, being quadratic. T is equal to 2 seconds, and t is equal to 4 seconds. So what are these solutions? Well, they're the solutions to both equations, therefore they must be the points which satisfy both equations, therefore they must be the intersection points. So we know that this is 2 seconds, we know this is 4 seconds. So we'll say that delta t, the time spent above here, is 2 seconds. And that's it, that's all there is to it. Draw that parabola if you see one of these things. It really helps to visualize it. So this was using kinematics, but not, it wasn't too strenuous. Now, the third question is just slightly trickier, and I've kind of painted myself into a corner.
It's not using the crop tool to deselect that and just use you find if you just select all of that space, if you just drag around all of that space,
Okay.
Yeah.
Ah, there we go.
and then move it. That's it.
Then
Perfect.
over here, because I want to talk a little more about the third question. So,
Just change the size. You can make this smaller as well if you want.
oh my word,
That, right?
it does make me look like I work meter. Okay, So that was question 1, that was question 2. So now we're looking at the third one. Now, your first instinct might be to kind of trace the question before backwards. So what they're saying is that we've got a different parabola because we have a different initial speed. So it's actually going to, if you think of the initial speed as the steepness of the parabola at the very beginning, that V0 would be the steepness right there. If V0 is different, it's going to be a different steepness. It's either going to be steeper or flatter. It's going to be a different parabola. It's going to have a different equation. So you could sit down and solve and try and work out this equation going backwards. However, it's just not worth it. It actually takes too long. I did have a go. So instead, let's be a bit more strategic. So they're saying let's draw a fresh parabola because we want to make sure we know this one is different. Let's make it look really, I can't remember if it's steeper or less steep, but say it's steeper. And again, we've got our 40, and we have some peak steepness. And now we know this delta t. So here we have delta t is given as the square root of 17 seconds. So if we're a bit clever, we can think, okay, we no longer know this, let's call it S prime. We no longer know the height of it. We can no longer say that it goes up 45 meters because it's a different parabola, so it's going to have a different maximum point. Now, if you had the equation of the parabola, no problem, you could find that maximum by differentiation. However,
I've already told me that's here. Sure.
However, we just don't have the information. So what we can do is think about just this little section when it's reached its peak and it's on its way down. So here it is again. And we know that this took the square root of 17 over 2. Remember, the parabola is symmetric. So that this time is equal to that time, and the whole time is square root of 17. So each time period must be equal to square root of 17 over 2. And we know that the only acceleration it's feeling, it starts out with velocity is equal to 0 up here, so the peak of its thing. And we know that the only force acting down, acceleration, and therefore force acting on it, is g. So we use our constant acceleration equation. Distance traveled, let's say delta s, change in position, just to make it clear that we're not talking about the actual absolute height or anything. We're just talking about the amount the position has changed vertically between here and here. Remember, it looks like a parabola, but it's actually only traveling up and down. It's not actually in a parabolic arc. So delta s, using our equation again, is equal to S0, but we'll take that to be 0. Velocity at the top times the change in time divided by 2. This change in time, so we'll take t1/2, plus 1/2 acceleration delta t 1/2 squared. Forgive the inconsistent notation. I hope it's clear. Well, v top is 0, so actually this is. Yeah, it's plus because we're now choosing this to be the positive direction. It doesn't matter. So it's 1/2 times 10 times 17 over 4, which is that squared. So now we know the difference in distance here, which I'll give it to you is 170 over 8. So we know that the total height is 40 plus 170 over 8. No problem. Now we can use conservation of energy again, happily. We know the height at the very top. Therefore, we know all the energy that the thing has at the very top. It's got no velocity, it's all potential energy. Well, when it's at the bottom, it's all kinetic and no potential. So we can just compare these two quantities. Same thing, 1/2 mv naught squared, where v naught is what we're looking for, is equal to mg h total. Masses cancel out, we never need them, and you can solve for v naught. No problem. So that one is a little more complicated because you have to use kinematics and conservation of energy. But it was simpler than trying to solve quadratic equations for times and things again, even though in previous questions that's what worked. Any questions so far? And do you guys want a break? Would you guys like
Do you
a...
want a break? I don't really mind. Do you want a break?
I'm fine.
You good? All right. Okay. If you need a break anytime, just say. Okay. Question 4. So this one's talking about power. So the key thing to remember is that power measured in watts is energy per unit time, or really more rigorously, dE dt. But you probably might need to use like infinitesimal powers in these questions. But it's the energy over time. So energy supplied to something over time, or the energy required over, divided by the time that's taken gives you the power. So it's measured in watts, and we can therefore know that watts are joules per second. The units always have to match on any side of an equation. So if you remember this, you're fine. Okay, so here's our setup. A nice flat plane, block sitting on it. What are the forces? Well, as always, we've got the mass, the weight, sorry, mg. And equally, our reaction force, which is equal to mg. Our driving force, let's say it's going in this direction, d. And that's the direction the friction force will act in, force of friction. So, they've given us force of friction, which is the resistance to transmotion. I mean, I can only think it would have to just be friction, but maybe there's lots of people studying underneath trying to stop the thing. They don't really make it clear. I'm just going to call it force friction because that's simpler. So now we're going to think about the work that is being done on this object. So the key equation for work, which we saw before, work, different to this watt, is force times distance. So therefore, of course, the force must be the work divided by the distance. We can also use that. So we can also use this equation. Remember that E, in this case, E is the work. So let's just express it as E over D. We also know that distance traveled is equal to the velocity times the time. That's like our simplest constant acceleration equation with no acceleration. So we can say that the power is equal to, well, actually, let's use this. Plug that in for energy. And then here, plug D is equal to, T is equal to D over V. E is now equal to force times distance. And this T is equal to distance over velocity. The distances cancel. You get FV. So that's the trick with this question, is that the power is equal to the force times the velocity. Or rather, the velocity is equal to the power of the force, or the force is equal to the power divided by velocity. So we get that the driving force is equal to P over V. And if you plug in the numbers, we get 4 times 10 to the 4 newtons. Okay, so a little clarification. I'm sure you guys have probably used scientific notation before. If you haven't, it's really straightforward. You'll get it picked up in a second. When you have things that with all these zeros hanging off the end, stick everything in scientific notation. You won't lose track of zeros. You won't lose track of powers. It just makes everything simpler. look out for a kilo in the units, little orders of magnitude hidden away over there. So that'll be 1,000, so it'll be 1.5 times 10 to the 6 watts. Stick everything into like basic SI units. You won't get lost. Okay, so we have our driving force. Now, what they're asking for is the acceleration. F equals ma comes to our rescue. So F net is here equal to the driving force minus the force of friction, the resisting force, which is equal to the mass times the acceleration. Just solve for A. We just worked out the driving force. They've given us the resisting force, the friction force, and we know the mass. Great. So the next one is just a simple reapplication of this. So most of the marks were for finding this equation. And in this case, they're talking about something at steady speed. So that means the acceleration is 0. Therefore, the forces must be balanced. So we use our equation for the driving force, set it equal to the resisting force, and solve for B. So we have P over B is equal to F friction. B is equal to over friction. So all that, the clue was steady speed. Steady speed, no acceleration. No acceleration, no net force. The forces must be equal. Okay. Is it okay? Okay. Pulleys. Ramps and pulleys. Classic mechanics. So again, always the best thing is to draw a diagram. Here there's a bit of a subtlety. We've got actually two situations happening. And you may be tempted to draw this in one like big tangled diagram full of arrows and things. Best just to separate them out. So this is how I would address it. We look first at particle B. Now, particle B doesn't know anything about particle A. All it knows is its immediate surroundings. It's sitting there. Let's draw it as a box. It knows that the only forces acting on it are its weight and the tension in the string. I'm not sure why there's not more colors. Okay, so about tension. Now, in a case where it's not moving, of course, tension will be equal to the mass times g. But we can also look at occasions where it is moving, in which case the tension is not equal to it. So that's B sorted. Let's look at A. Now, A is a little more complicated. It's got this ramp going on. So we're going to draw our normal ramp diagram. Here she is. All the usual forces are acting on it. Into the ramp, we have MAG cosine theta, and exactly the same coming out of the ramp. We say R. Down the ramp, we have MAG sine theta, and we have the tension in the string. We also have the force of friction, but we can't draw it in yet because we don't know which direction it's acting, because we don't know which direction the thing is going to start to move. I'll just clarify that this was the original weight going down, mg, and we've now resolved it. It's called resolving along those axes. So if we want to, this diagram is not complete. We want to work out which direction does friction act? Well, let's just for a second imagine that there is no friction, which at the very beginning, when it's just starting to move, but it, like in this infinitesimal moment where it's been accelerated, but it hasn't actually started moving yet, there is no friction, because friction only happens when you're moving. So this is a perfectly legitimate approach to take. So in that scenario, the only force acting on A, the only forces acting along the ramp are its weight pulling that way and B's weight pulling that way. Because at rest, at that infinitesimal moment, tension in the string is equal to MBG. So we're given the masses of the particles. So let's just pulling down here is MA G sine theta, and pulling A that way is the weight of B pulling down, which is MB G. Well, MA is 0.26. Sine theta can never be more than 1. So the best it's going to do is give this thing to be, the mass to be 0.26 times G. In fact, it's probably going to, theta is not 0, so it's actually probably going to reduce this whole expression by a bit. So we're going to have something like, so 0.26 times 10, 2.6 sine of theta. Oh, actually it's alpha here, but 5/13. Well, that's a lot less than 1. So this thing is going to be less than 2.6. Whereas this thing is fully equal to 5.4. So so at that very moment, the net force is acting up the hill. Right, great. So now we know that the force of friction is going to be acting like that. And our diagram is complete. So we also know that the force of friction is equal to mu r, which is equal to mu ma g cosine. I'll keep calling it theta, even though it's alpha in the question. Usually angles are given Greek letters. Theta is the default one. So now we need to look at the actual forces involved. And in the first question, they're asking for the magnitude of the acceleration. So we know all the forces here. The key thing to realize is that this T and this T are the same. They have to be the same, and why? Because the string is inextensible and taut. Blah, blah, blah. So if you had some like super stretchy elastic string, all kinds of nasty, exciting things would be happening. But we don't have to worry about this. You can think of it as just perfectly stiff, except that it's got a bend in it. So these two tensions are the same. So we need to derive two expressions for the tension. Let's look at B first. B again. The net force on B. Acting up and down, of course. And let's say that down is positive in this case. So let's say that down is positive for B, which also corresponds to up the ramp for A, because that's the way we're moving, so it's more convenient for us to talk about that positive. You can talk about the other way, you just have to be consistent. And you'll end up with like a negative acceleration. You just know that that means you're actually going uphill. But we want a positive acceleration, so let's say that uphill and then down the steep slope is down the cliff is the positive direction. So the net force on B is T minus MBG. No problem. Now this is going to be equal to, you guessed it, MBA. Newton's second law coming in. So let's get this in terms of T. T is equal to MBA plus MBG. Well, that wasn't too bad. So let's look at A now. So we're looking at the net force on A along the ramp. And we don't care about what's going up and down. Those things are not going to be changing. They're not affected by the pulley. They're in independent direction. So the net direction with up the ramp being defined as positive. So T, again, minus MAG sine theta which is the component of our weight that's along that direction, and minus the force of friction. And this gives us T is equal to blah, blah, blah. Oh, sorry, that should be equals MA. Now these A's are the same. Because of the string is taut and inextensible, they have to accelerate at the same. If you can think of like if you thought of two ball bearings connected by a stiff rod that can move in one direction, how can you, and this rod can't be squeezed or squished or, hang loose, it's just a stiff rod. How can they have different accelerations? They have to always be moving in tandem. The same is true of this, because it's the simplified example where the string is kind of like a stiff rod, except it's got a bend in it. So these A's are the same. So here we have two equations and two unknowns. So it's a general rule that if you have a set of equations with unknowns, x, y, z, various quantities, you need the same number of equations as you have unknowns, otherwise you cannot get a full solution. You always end up with something in terms of something else. So if I was solving for x, y, and z, I would need 3 independent equations relating x, y, and z. Here we need a and t, and we have 2. So we go through our usual procedure. You set, you find what t is here in terms of a, and you set that equal to this t. You solve for a in terms of ma, which we have, g, which we have, sine theta, which we have, force of friction, which we have, ma, which we have, mv, which we have, blah, 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 blah. We'll get a number for a, no problem. Then you just need to plug it back into this equation and you get t. And that's that whole sub-question. So you can see the importance of drawing these diagrams. They really help you keep track of everything that's going on. Now, the second one is actually quite short. Find the distance moved by each of the particles. Kinematics again. We have our acceleration, which turned out to be 4.9.
I'm going to go quickly. I'll be back in a minute.
Sure.
Just a minute.
So now for part 2, we use our little kinematics equation. Distance traveled is equal to v naught t plus 1/2 at squared. Well, v naught is 0 because we're starting from rest. So this is equal to 1/2 a t squared. We have a, we have t, we get s. Now, I just did this in general, but let's say I was just thinking of object A. This is true for both of them. Look at it. The time is the same, the acceleration is the same. It's got to be the same distance moved for either of them, which makes sense with this kind of rigid string, which is a bit like a rod. How could these guys ever move different distances? The rod would have to be squished or something like that, which is not allowed. And that's all there is to it. So we get 0.39 meters. Okay, do you guys want a break?
Yeah, I'm going to do it quickly. Yes.
Yeah. You grab some water.
It's your news.
Hello.
Oh, great.
You're here to this undergraduate French classes and all.
Yeah.
Guess what? We sold
Yeah.
Yeah, you bet. We're gonna use the money for people table. if there's anything left to keep, but if there's not, that's better. And we're looking for income table. So we've got 140 pounds.
Yeah, and they should be able to
Well, yeah, maybe we'll see. Yeah, that's what the
How do they get advice?
I'll recommend. Oh, God.
There's more of the
Yeah. Yeah.
Yeah, that's right. I think I've seen more so
I used to. Right? Yeah, absolutely. Yeah.
Okay. So this setup, it's another one of those balance forces. There's a little bit of subtlety, but let's first just start off with all the things that we know. We're told that P is an equilibrium. So that means all the forces must be balanced, and they've already drawn in these very convenient axes. I will emphasize that this is us looking down on an object. So its movement horizontally along this plane that we're looking down on is not going to involve mass just yet. Like, we're just looking at these forces that they've given us. So the net force in the x direction, well, that is going to be this component of beta plus, well, I call it beta, the 2.5 Newton force, plus that component of alpha and that component of the F force. So what that means is that we've got, in the positive x direction, 2.5 cosine beta plus 2.6 cosine of alpha. And then the F force, it's got a negative x direction. So we go minus F, which is magnitude force, cosine theta. Exactly the same thing happens in the y direction. 2.5 sine of beta, so we're talking about this component, minus 2.6 sine of alpha, because it's actually acting downwards, plus f sine theta. We know that both of these are equal to 0, because this thing is in equilibrium, so there cannot be any net force in either direction. But at initial thought, this doesn't actually seem to help us that much, because we've got so many unknowns here. We don't know what cosine beta is, we don't know what f is, we don't know what cosine alpha, cosine theta. What we're given is the tangent function of these angles. And just a little bit of thought will tell you that you can work out the sine or the cosine. Just using your calculator, you can go sine of the arc tangent of something. So let's say we wanted the sine of alpha. It would be the sine of inverse tangent or arc tangent of 1205. Now that's the simple way of doing it. I'd like to give you a little more intuition. Is now, you've learned about trigonometric functions as being the ratios of different sides of a right angled triangle. So let's think of this tan of alpha is 12 over 5. Well, this alpha, this fact says nothing about the magnitude of this actual force. It's just a relation, it's just a ratio between sides. So it's going to be true for an infinite number of similar triangles where the ratio of the sides is the same. Because you can always take those sides and multiply them by 10 or 15 or whatever. Any scaling of that triangle, i.e. any similar triangle, is going to have the same tangent of that angle. So imagine that we had this triangle where this side was 12, so tangent is, so let's say we've got alpha, yeah? So the tangent of an angle is opposite over adjacent. So this is like this is a triangle for which the tangent of alpha would be 12 over 5. And the hypotenuse, in that case, would be 13. It's one of these like special ones where everything's an integer. Now we know that this is similar to a triangle with the hypotenuse of 2.6. So therefore, let's look at we want the x component. So let's call this f alpha x. So we know that f alpha x over 5, so divided by this one, must be equal to 2.6 over 13. It's the ratio of the sides, and thus you can solve. So you can just get this, you can straight away get the force. Or alternatively, you could just look at this triangle and say, well, if it's similar to my actual triangle of forces, then the tangent is the same, so is the sine and the cosine. So I can just lift the cosine and the sine straight off that triangle. Sine opposite over hypotenuse, 12 over 13. So if I'm given a trigonometric function, you know that you can get any other trigonometric function just from that. Through your calculator, just by using that, no problem. Or realizing that it describes an infinite family of similar triangles, and once you have one of the trigonometric functions, that essentially fixes two of the sides, and therefore the third one is fixed because this is a right angle triangle. So all the information is known about the ratios of those sides.
Can you use Pythagoras here to find out what the value is in the x direction and the y direction by I don't know how to explain it. So can I write somewhere? Or?
Sure, absolutely.
I'm not sure. I've never done it this way because.
Okay.
Okay. So you've got 2.6 as a magnitude.
Well, do you want to write it on here so that people online can see it? Yeah. You can see the screen here.
Okay. Oh.
Yeah, it doesn't have an accelerator, so you have to sort of keep it accelerated.
Okay, that's supposed to be 2.6.
Okay.
Right.
You can work out if you need to.
Huh?
You can work out if you need to.
Yeah. Okay. And this is. Wait, what does it say on the page? No, sorry. 12 and 5, right? What's
the
tan?
similar one. So
12
tan
and
is
5,
12
yeah.
and 5.
Okay. So then you would have 5. So you could do.
That's not true.
Or could you not do this?
What is this x?
X is so
Is the ratio.
the ratio is 12 and 5. So 12 times x would be the distance here, and 5 times x would
Right,
be the
so-
distance there.
Well, x in this case would be this would work. So this implementation of Pythagoras would work if x was a ratio that measured the ratio between this and this, these two similar triangles. So this is not a true triangle. If you had 5, 12, and 2.6, that would not be true.
Yeah.
Because if you have 5 and 12, the hypotenuse has to be 13 because it's a right angle triangle. So if you go square root of 5 squared plus 12 squared, you would get 13.
Okay.
So this is not a true triangle. You could say this could be a technique where you go 5x
Yeah.
and 12x.
Yeah. Exactly.
In which case, this x would be you'd need it so that like 5x would be the ratio. 5x is equal to the actual fx.
Yeah. Exactly. Yeah.
So x is equal to the ratio between the actual fx and the one on the sample similar triangle.
Okay.
So you'd need the ratio first.
Okay.
And that's kind of how we've done it here. So the ratio is the same for any individual side if you compare it to the same side.
Yeah.
So we know that that is equal to 2.6 over 13 because we already used the sample
Okay.
triangle calculated hypotenuse. And it's a very similar idea.
Yeah,
It's a
okay.
different way of looking at it.
Yeah.
Yeah.
Just a question, please.
Sure. Do you mind if I
Yeah. Don't mind at all.
But yeah. So now we have all the information we need. We have two equations, and we know what 2.5 is. We know what cosine of theta is. We know this, all good. We don't know what theta is, or by extension tan of theta, and we don't know what f is. But we've got two equations, so no problem. So our first step. Our first step is to. So I'm not gonna calculate this for you. Like it's just multiplying a bunch of numbers together. But the first thing is let's say that f cosine theta, and we worked it out to be some number a, and f sine theta, we worked it out to be some number b, which is just from these guys, which are all numbers that we now know. Now, if we take that f sine theta over f cosine theta, which is equal to b over a, well, this is just equal to f's cancel, tan of theta. No problem. Now, we can simply plug that back in. I mean, it's the simplest thing in the world to then go f is equal to b over sine theta, and then use our calculators and be a bit cheeky and just go, no problem. And that gives you the correct answer. So I went into detail about these, but really you can just use your calculator, use the inverse tangent, the arctan, to get the value of theta and then plug it into the sine function. You have no problem at all. Okay, so there's another little bit to this question. Is now imagine that f is removed. And they're asking, how will the thing move? Well, obviously, if it was balanced before and that one of the forces has been removed, it's going to move. There's now a net force, also no longer zero. If there's a net force, there is acceleration. And there's acceleration of this, the net force is going to be of the same magnitude as the force that was removed, right? Because the object is now going to be sitting here with some net force acting on it. Well, if I then, put the F back, it would be like that, and it would balance, and the thing would be still. So the net force must be in exactly the opposite direction that F was, and of the same magnitude. So F, which we've already derived, F net is equal to the F that we derived, which is equal to the mass times acceleration. Good old Newton coming in there again for us again. Acceleration is equal to F over m. We have m, we worked out F, no problem. Now they're asking for the direction, so it's going to be in exactly the opposite direction that F was. And from our drawing, we know this was theta, therefore that must also be theta. So you can just write that as, so many degrees clockwise from the positive x-axis. So that the information is the number of degrees, which axis it's sort of subtended from, and which direction the angle is. So you don't want to be talking about a theta that's over here, or a theta that's there, or anything like that. You want to specify which axis you're talking about, which direction it's going, and theta. Draw a little diagram, just so that they know that you got it right. They give marks for strange things. And that's it. So you already have theta, by the way, you have tan of theta, so you can just use inverse tan. Okay, we've got 10-15 minutes left, and I'm going to have a go to completing the last question. Now, kinematics, again, our favorite, but this time not the constant acceleration equations. Oh, why is that? Well, look at this equation, this horrible zero full equation they've given us here, which I'm going to now re-express as 1.17 times 10 to the minus 5. 1, 2, 3, 4, 5. And then the same thing again. Well, it's got t to the third and t to the fourth here. Now, constant acceleration equations imply that the distance traveled is going to be only a quadratic function of t. Remember, it's S0 plus Vt plus 1/2 Vt squared. That's it. There are no further terms. There's no cubic terms and no fourth power terms. So this cannot be under constant acceleration. Something else, more funny is going on. So this is going to involve some differentiation, which I'm sure is no problem. So they want you to find the distance AB. So what does that mean for us? We need to know the time that it starts, time 0, and the time that it finishes at point B, and then plug that into our distance equation. So what do we know about being at point A and B? Well, we know that it's at point A, it's at rest, and at point B, it is at rest. So the velocity is 0 at both those points. So our first job is to find out an expression for the velocity. In fact, I'm actually going to re-express this because I don't want to keep writing this thing. I'm going to call that C for constant. So the velocity, let's be super rigorous here and say velocity, function of time, is equal to ds of t dt. And there's a lot of notation. This is also often written as s prime of t. But in the case where the dependent variable is time, in physics you often use what's called a dot. And s dot means s differentiated with respect to t once. S double dot, d squared less dt squared. S triple dot, it goes on and on. Now, this is some straightforward differentiation of a polynomial. C doesn't change, and we get, from this expression, 3 comes down, 1200 t squared minus 12 t cubed, which we can factorize as 12c times t squared, take t squared out, 100 minus t. So when is this 0? When t is equal to 0, point A, great. And when t is equal to 100 seconds, point B. There we go. That's what we needed. Now, you can do this yourself. The distance AB, they've given us, this is our expression for the distance traveled as a function of time. So after 100 seconds, it's going to be this number times 400 times 100 cubed minus 3 times 100 to the power 4. Easy. Now, in the second part, they want to find the maximum speed of the car. So we worked out, we have an expression for speed or velocity, is this one. So how do you work out the maximum of something? Any ideas?
The stationary point,
Exactly, and what's the condition for a stationary point?
the tangent is 0 at the station.
The tangent?
The gradient
Right, how do you get the gradient?
by differentiating.
And is that all that a maximum needs to satisfy in order to be a maximum?
No, it could also be a minimum.
Right.
So you would have to differentiate again. And if it's smaller than 0, then it is maximum.
Very good. So I'm just going to write that out. So I'm going to do a general function, f of x has a maximum when f prime of x, so f of x differentiated once, is equal to 0, and f prime prime of x is less than 0. Minimum is the opposite. Inflection points are something slightly more tricky. We'll get to them in a second. So all you have to do is find v prime of t is equal to 0. This gives you two values of t. Then you calculate v prime prime of t. And you evaluate it at, so let's call this a or b. And then you test each one, v prime prime of a, question mark, greater than or equal to 0 or less than 0, v prime prime of b, well, what is that in relation to 0, and you find which one. So there'll be, in fact in this case there'll be two stationary points. One will be a maximum, one will be a minimum. So for a minimum, f prime prime of x is greater than 0. It's exactly the opposite test. 3, you find the acceleration of the car. So we've, as it starts from a, well, the acceleration, that's just the second derivative, as we've seen before. That is that, we already worked out an expression for that. In fact, I'll just write it down so we can look at it. Acceleration is s, sorry, actually it's not v prime prime, it's v prime. Sorry, it's the second derivative of position, it's the first derivative of the velocity. So this is s prime prime of t, which is equal to v prime of t, a sort of chain of little differentiations going on. And this is equal to c times 2400 t minus 36 t squared.
Nearly done?
So we see that at a, the time is equal to 0, therefore the acceleration is equal to 0. And at point B, the time is equal to 100, and you get, in fact, you get some fairly large number, which is an acceleration that's less than 0. It's decelerating, which makes sense. The thing's slowing down, coming to a stop at the end. Now, in the very final part, they want us to draw a diagram of this car's motion. In fact, of its velocity versus the time. So we've got to sit back and think what information we have. It's just a sketch, so we don't have to be precise. We don't need to label the points on the thing. We have to have a general idea. So, data. What do we have? Well, we have that the velocity, so this is what we're graphing, velocity versus time. This is its equation. 12c times t squared times 100 minus t. So where does this equal 0? Well, it equals 0 when time is 100 And when 100 seconds, then when time is equal to 0, as we found before. But here, it's kind of 0 twice at t squared. So this is what's called a double root. And you'll see it crop up when the function is meeting the x-axis tangently. So instead of just cutting the x-axis like so, which is the case for this one, which is called a simple root, something that's a double root is one where it's kind of like that. So those are when your quadratics will have like x minus 3 squared. That means it just touches the axis. So our thing will have 3 zeros, which make our velocity graph, which makes sense because it's a cubic equation. If you look at our first expression for it, it was t squared minus 12t cubed up there. I've just now taken the t squared out, but it's still a cubic equation. So cubic equations tend to look something like that. They'll have 2 peaks, 2 kinks in them. So this one will have one double root and one simple root. The double root at 0 and the simple root at 100. So we know that even our thing kind of comes up. So at 0, it doesn't just come up shooting. We know that the velocity, that the acceleration is 0 at that point. So it's a really gentle increase in velocity. In fact, at time equals 0, it's not really accelerating at all, like at that very, very moment. The slope of the velocity is 0 at that point. So it's got to kind of start off coming in like this, right? It's not just shooting straight up. And that makes sense. So we can kind of project this equation back. The equation is just for a cubic equation. It doesn't know that you can't have negative time. So it'll continue, but we just won't care about it because we're talking about a physical thing. It'll kind of touch the x-axis at that point and then start gently increasing. So we know what the beginning of this looks like. Now we found a maximum at some time, which I will tell you is 66.6 recurring. So here's time 100, where we know that we just simply just cross in the normal way, plunge down through the axis, and maybe our function will continue there. And we know that around about here is our maximum. So the maximum is closer to the end than the beginning. And that actually, I don't know why I got it so small, but
Beautiful.
that's actually, okay, that's fine.
Just make it bigger.
I can actually. Oh God. Oh well. The one little thing I might mention is that if you do the test to find a place where the second derivative is equal to 0, you will get this point, which is like 33.3 recurring. So inflection point satisfies the equation f prime prime of x is equal to 0. So it's neither a maximum nor a minimum. It does not have to satisfy that the first derivative is 0. As you can see here, the curve is non-zero, but it indicates a place where f prime prime is changing sign, i.e. passing through 0.
So the shape of that curve is going for an inward curve and then to an average curve at that point.
It's coming out of a minimum and it's going towards a maximum. So the second derivative at this minimum was positive, and at the maximum it's negative. At this point, the second derivative is 0.
Brilliant. All done?
Yeah, that's it.
Fantastic. I forgot because I wasn't in here. Did you manage to get the breaks? Did you have no breaks? Did you go straight to
We're on break.
Okay, all right.
I often thought they were very committed.
Yeah. Good. Thanks ever so much for that. Brilliant. I was watching it upstairs. I had a meeting, but yeah, it was